Okay, I want to take the opportunity to kind of walk through this simulation. So I shared this file with you, and I want to show you how it works, and you can play around with it. And so this was the idea that we've got a game that's paying out $100 every time you roll a 5, and so what happens if you roll it 36 times, 1,000 times, and then one time, like certainly you could win 100 or not. We asked that because we talk about the average, and so it's the average that is the expected value. So let's look at the simulation. So what I've done here is like just made up a PowerPoint, and so this says roll the die 10 times. I just want to take you through the columns so you understand what's happened here. So Excel is really just a way to organize a chart, but also has some nice functions that we can use for probability. So these are the roll numbers. It's just 1 to 10, and we're going to roll it more than 10. We'll start with 36. Die 1 is generated by a random number between 1 and 6. Die 2 is generated by a random number between 1 and 6. And then after you type that formula, which has to have an equal sign, you can actually just pull down the little blue thing, and it will actually bring it down as far as you want to go. And so if I want to roll the dice more, I would roll the dice more. So I'm going to go back and just roll the dice 10 times. The sum just adds up those two columns, so B2 and C2. And then again, if I pull this down, it will reference to B11, C11, so I don't actually type this each time. So that's the sum. And then this is like kind of like a summary table, so you know that like a 1 can't happen, so we start with a 2, and then how many times it comes up. And so this is a little bit more advanced Excel. It's a Google spreadsheet, but it's Excel. It counts the column D if it's a 2, so it counts it. D to D is just the column, and then because you can put in a range that you want to count. And then if it's a 2, and then so far it just goes down, it counts it if it's a 3. So I'll tell you and then it'll just kind of check to make sure we've only got 10 rolls. The experimental probability, what it does is it divides each one by 10, so the total. And as that number changes, the nice thing about that number is if I roll it 36 times, that number will become a 36. The theoretical probability is what we actually happen from the chart. So 1 out of 36, 2, 3, 4, 5, 7 as a 6 out of 36 chance. And then we just compare the two. And then there's a chart here to show the expected and the experimental. And so we know that rolling a 5, so the question was rolling a 5. If we roll a 5, which is the outcome here, that has 11% chance. So if you are giving out $100, the chances are that if we multiply the 5 by the theoretical probability, of rolling a 5, which is 11%. So we on average pay at $11.11 each time, and so we'll see how that works. In this case, a 5 came up twice, so every time it rolls the dice again. 5 came up twice, so we actually pay $200 divided by 10, and so we've actually paid $20 per time. And so we expect to pay out $11 each time. We'll see how that works. So what I can do is highlight all of these columns here. And every time when I pull this down, it'll roll it, say, 12 times. And then I can pull it down to roll it 36 times. So this is a simulation without actually having to roll it. That's how this is set up. Okay? And so experimentally, we've actually rolled 3 5s. Oh, it's only done 35 times. So one more. So it counts 36 there. This goes down if it knows the sequence. So in this case, we've rolled 5 5s experimentally. Those all regenerated as every time I change it. So 5 5s experimentally, we actually don't pay out $11 each time. We paid out, let's just pull out a calculator. We paid out 500 divided by 36, which is $13.88 every time. We're expecting to only roll it 4 times. We've rolled it 5 times, so we paid out a little bit more. Okay. If we roll it 1,000 times, I know what you're thinking, and Mr. Dan, you're really going to roll the dice 1,000 times? And I tell you, absolutely yes. We're going to roll the dice 1,000 times. And so we just keep going, and drag it down till we get to 1,000 or 1,001 for the first one. I totally messed that up. Once you see 1,000, just let go. Okay, so it rolls it 1,000 times. I generate, so that's 941. Let's just do a little bit more. So I think 1,001 is what we want. And so we roll the dice 1,000 times, and we can see the 1,000 possibilities. We've got 101 outcomes, so we paid out 101. Let's just use a calculator so it doesn't regenerate. So we paid out 101 fives times $100 divided by 1,000 times. So we paid out about $10 each time. Okay, and so this is what the expected value is. 1,000 times, we expect actually to pay out $11 each time. So the casino is actually up right now. It's only paying out $10 each time. If we do something different, very, very quickly it'll change everything. And so if we paid out 116 times, you can see how it in a different 1,000, 116 times 100 divided by 1,000, we paid out $11.60 each time. The casino doesn't care about any of this. Sometimes they pay $11.60 in a group of 1,000. Sometimes they pay out $10 in a group of 1,000. The reason why they don't care, and let's just see if we change it again. We pay out 110. I think we actually got that. We're always getting around that 11%. And so we can see this is 10.7. If we change it again, that's 11.7. 12.4. That's the players getting really lucky. 12.8. The nice thing is we don't care about any of that because we're actually going to charge not $10 each time, not $11, probably not even $12 each time. We'll probably charge like $13, $14, $15 each time. So as long as that number stays below what we charge, there the consumer's really getting lucky. But that's only one group of 1,000 because for every other group of 1,000, it's well below. And so that's how it works, and that's how we kind of run a simulation with Excel. You poke around in this file, it's really interesting. As you roll the dice more, it looks more and more similar to this, and we will discuss that in the next coming days.